In the previous video, we gave a mathematical definition of the cost function. In this video, let's look at some examples to get better intuition about what the cost function is doing and why we want to use it. To recap, here's what we had last time. We want to fit a straight line to our data, so we had this form as a hypothesis with these parameters theta 0 and theta 1, and with different choices of the parameters, we end up with different straight line fits to the data, h of x like so. And there's a cost function, and that was our optimization objective. For this video, in order to better visualize the cost function j, I'm going to work with a simplified hypothesis function, like that shown on the right. So I'm going to use a simplified hypothesis, which is just theta 1 times x. You can, if you want, think of this as setting the parameter theta 0 equal to 0. So I have only one parameter, theta 1, and my cost function is similar to before, except that now h of x, that is now equal to just theta 1 times x. And I have only one parameter, theta 1, and so my optimization objective is to minimize j of theta 1. In pictures, what this means is that if theta 0 equals 0, that corresponds to choosing only hypothesis functions that pass through the origin, that pass through the point 0, 0 over there. Using the simplified definition of a hypothesis and cost function, let's try to understand the cost function concept better. It turns out there are two key functions we want to understand. The first is the hypothesis function, and the second is the cost function. So notice that the hypothesis, right, h of x, for a fixed value of theta 1, this is a function of x. So the hypothesis is a function of what is the size of the house x. In contrast, the cost function, j, that's a function of the parameter theta 1, which controls the slope of your straight line. Let's plot these functions and try to understand them both better. Let's start with the hypothesis. On the left, let's say here's my training set with 3 points at 1, 1, 2, 2, and 3, 3. Let's pick a value of theta 1. So I'm going to set theta 1 equals 1, and if that's my choice for theta 1, then my hypothesis is going to look like this straight line over here. Okay? And I want to point out, when I'm plotting my hypothesis function, my x-axis, my horizontal axis is labeled x, is labeled, size of the house over here. Now, I've temporarily set theta 1 equals 1. What I want to do is figure out, what is j of theta 1 when theta 1 equals 1. So let's go ahead and compute what the cost function is for, the value 1. Well, as usual, my cost function is defined as follows, right? Sum over my training set of this usual squared error term. And this is therefore equal to this of theta 1 xi minus yi. And if you simplify, this turns out to be that 0 squared plus 0 squared plus 0 squared, which is, of course, just equal to 0. Now, inside the cost function, it turns out each of these terms here is equal to 0 because, for the specific training sets I have, where my 3 training examples are at 1, 1, 2, 2, 3, 3, if theta 1 is equal to 1, then, h of x, right, h of xi is equal to yi exactly. Let me write this better. Right? And so h of x minus y, each of these terms is equal to 0, which is why I find that j of 1 is equal to 0. So we now know that j of 1 is equal to 0. Let's plot that. What I'm going to do on the right is plot my cost function j. And notice, because my cost function is a function of my parameter theta 1, when I plot my cost function, the horizontal axis is now labeled with theta 1. So I have j of 1 is equal to 0. So let's go ahead and plot that. Going to end up with an x over there. Now let's look at some other examples. Theta 1 can take on a range of different values, right? So theta 1 can take on negative values, 0, or positive values. So what if theta 1 is equal to 0.5? What happens then? Let's go ahead and plot that. I'm now going to set theta 1 equals 0.5, and in that case, my hypothesis now looks like this. There's a line with slope equals to 0.5, and let's compute j of 0.5. So that is going to be 1 over 2m of my usual cost function. It turns out that the cost function is going to be the sum of squared values of the height of this line plus the sum of squared of the height of that line, plus the sum of squared of the height of that line, right? Because this vertical distance, that's the difference between, y, I, and the predicted value, h of xi, right? So the first example, this is going to be 0.5 minus 1 squared, because my hypothesis predicted 0.5, whereas the actual value was 1. For my second example, I get 1 minus 2 squared because my hypothesis predicted 1, but the actual housing price was 2. And then finally, plus 1.5 minus 3 squared. And so that's equal to 1 over 2 times 3 because m, my training set size, right, I have 3 training examples. And then that's times, simplifying the thing in parentheses, is 3.5. So that's 3.5 over 6, which is about 0.68. So now we know that j of 0.5 is about 0.68. Let's go and plot that. Oh, excuse me, math error. This is actually 0.58. So I'm going to plot that, which is maybe about over there. Okay. Now, let's do one more. How about if theta 1 is equal to 0? What is j of 0 equal to? It turns out that if theta 1 is equal to 0, then h of x is just equal to, this flat line, right? That just goes horizontally like this. And so measuring the errors, we have that j of 0 is equal to 1 over 2m times 1 squared plus 2 squared plus 3 squared, which is 1/6 times 14, which is about 2.3. So let's go ahead and plot that as well. We end up with a value around 2.3. And of course, we can keep on doing this for other values of theta 1. It turns out that you can have negative values of theta 1 as well. So if theta 1 is negative, then h of x would be equal to, say, minus 0.5 times x, right? If theta 1 is minus 0.5. And so that corresponds to a hypothesis, with a slope of negative 0.5. And you can actually keep on computing these errors. This turns out to be, for 0.5, it turns out to be a really high error. It works out to be something like 5.25. And so on. And for different values of theta 1, you can compute these things, right? And it turns out that you compute a range of values, you get something like that. And by computing the range of values, you can actually slowly trace out what this function, j of theta, looks like. And that's what j of theta is. To recap, for each value of theta 1, right, each value of theta 1 corresponds to a different hypothesis or to a different straight line fit on the left. And for each value of theta 1, we could then derive a different value of j of theta 1. And for example, theta 1 equals 1 corresponded to this straight line fit through the data, whereas theta 1 equals 0.5, this point, shown in magenta, corresponded to maybe that line, and theta 1 equals 0, which I'm going to show in blue, that corresponds to this horizontal line, right? So for each value of theta 1, we wound up with a different value of j of theta 1, and we could then use this to trace out this plot on the right. Now, you remember, the optimization objective for our learning algorithm is we want to choose the value of theta 1 that minimizes j of theta 1, right? This was our objective function for linear regression. Well, looking at this curve, the value that minimizes j of theta 1 is, theta 1 equals to 1. And lo and behold, that is indeed the best possible straight line fit through our data. By setting theta 1 equals 1, and just for this particular training set, we actually end up fitting it perfectly. And that's why minimizing j of theta 1 corresponds to finding a straight line that fits the data well. So, to wrap up, in this video, we looked at some plots to understand the cost function. To do so, we simplified the algorithm so that it had only one parameter theta 1, and we set the parameter theta 0 to be equal to 0. In the next video, we'll go back to the original problem formulation and look at some visualizations involving both theta 0 and theta 1, that is, without setting theta 0 to 0. And hopefully that will give you an even better sense of what the cost function j is doing in the original linear regression formulation.